This video is a general introduction of the modern periodic table and includes some of the basic terminologies and characteristics that we would need to be familiar with to understand the modern periodic table in greater detail. The modern periodic table is divided into groups and periods. We are aware that the vertical columns are named groups or families, while the horizontal rows are called periods. So the modern periodic table has 18 groups and 7 periods. Let us look into the periods in greater detail. The first period consists of only two elements, that is, hydrogen and helium. So this is called the very short period. Now, looking at the next period containing 8 elements, periods 2 and 3, they are called short periods. Both periods 4 and 5 have 18 elements each and are called long periods, while periods 6 and 7 are called very long periods because they include 32 elements. Two rows demarcated separately in the periodic table also belong to periods 6 and 7. The row starting with lanthanum would be the third element in period 6, where there is an empty space left for the whole series of elements which follow lanthanum. This series is called lanthanides, and the one which follows actinium is called actinides. The lanthanides are members of group 6, while actinides are of group 7. Now to divide the modern periodic table into blocks based on the subshell that hosts the last valence electron. Groups 1 and 2 form the S block, while groups 13 to 18 form P block. We have 3 to 12 D block, which is sandwiched between S and P, and below is the F block. Now let's get familiar with some of the most important groups and families. Look at group 1. Apart from hydrogen, which is a nonmetal, all the other elements are metals. They are called alkali metals because when dissolved in water, they become strong alkalis. Group 2 elements are dubbed alkaline earth metals. The reason can be traced back to calcium, which during the early days was obtained as calcium carbonate, which is our chalk or marble, or calcium oxide, which was called quicklime. Calcium oxide was called earth at that time, and eventually all these elements in group 2 were called alkaline earth metals. Then moving on to the oxygen family. Group 16 members are called chalcogens. The word comes from the Greek chalkos, which we take it to mean as ore formers. This is because most ores are generally oxides or sulfides, which are found in the earth. Group 17 are the very famous halogens. They are the most reactive nonmetals out there. They are named so because they generate salts during their reactions. And we have group 18, which are the noble gases or inert gases. Apart from helium, all the noble gases have fully filled 8 electrons in the outermost shell. Now let us write the group numbers to these 18 groups and discuss some of the basic commonalities in these groups or families. So we have group 1 and 2 in S block, 3 to 12 in D block, 13 to 18 in P block. Now let us go about observing the outermost shell, which is filled in these groups. So for that, let us use our principal quantum number to denote the values of the energy levels, where period 1 gets n equal to 1, and second period will get n equal to 2 values, and so on. Now when we write the electronic configuration, we would see that all the elements in group 1 end with the outermost sublevel S, and it has configuration with S1. For example, hydrogen is 1s1, lithium is 1s2, 2s1, sodium would end in 3s1, and so on. So the electronic configuration can be generally mapped as ns1, with n taking on integral values as the period increases, being the principal quantum number. Similarly, group 2 would end with 2 electrons in the s sublevel, making the general configuration ns2. Helium with configuration 1s2 should have been placed right next to hydrogen here, but it is placed in group 18 owing to the fully filled shells and being a noble gas. Now, we know that in period 2, 2D doesn't exist. So after S, we go on to group 13, which is the beginning of the P block. It would have the configuration of NS2 NP1. So you can pause the video and write the electronic configurations of boron, aluminium, and gallium to clearly understand the same. Similarly, group 14 would end with ns2, np2, and so on, where one electron would increase in the p orbital, moving up to group 18 with ns2, np6. In n equal to 4 period, we see the 3d sublevel, and d electrons are going to be successively filled in them. The values would be n minus 1 d values going from d1 to d10. While in F block, F orbitals are successively filled from 1 to 14 in n-2 F orbitals. Now we have confirmed the basis of classifying the elements in blocks S, P, D, and F blocks, where the valence orbitals are the basis where we classify them into the same. Finally, looking back to the number of valence electrons in each group. In group 1, we see that it has one valence electron in the outermost shell. So they tend to lose one electron and form ions of charges +1. So this way, we could also talk in terms of valency for the S block and the P block elements. Group 2 would have 2 electrons in the valence shell and would form charges with +2 charge. Moving on to P block, group 13, we have both S and P sublevels, which form the valence shell. So group 13 has 3 valence electrons. And so on, where group 17 finally would have 7 valence electrons and group 18 would have 8 valence electrons. And we could try calculating the valencies of the same. The last terminology that we need to know is transition metals, which is the D block elements, and the F block elements are called the inner transition elements. The transition elements basically transition between the S block elements and the P block elements. That is, going from being metals to displaying properties of nonmetals. The S and P block elements are called the representative elements. So that's the general introduction of the modern periodic table. Happy learning!